Yeah, welcome. Today I would like to present Pearson's theorem. And it says the following thing: if A, B are self-adjoint operators on some Hilbert space H, and we assume that they have the same domain, so the domain of A equals the domain of B, and then this theorem says that if the operator C, which is defined as AJ minus JB, if this object is a trace class, so if this is in this trace class B1 of H for some given operator J, which is a bounded linear operator, then the theorem says that in this case the following wave operators, omega plus minus A, B, and now they are a little bit modified because this operator J enters the game in the following sense. This is defined as the strong limit for t going to plus or minus infinity exponential ITA. And now here we have this J in between, J exponential minus ITB, and here the projection PAC of B. These operators then exist. And in my introduction, I also explained that our goal is to prove the Kato-Rosenblum and Kuroda-Berman theorem, which handles the case that either the operator A minus B is trace class, or we have this thing here for the resolvents. In order to obtain existence and completeness of the wave operators. And this will then follow from Pearson's theorem when we said here J is simply the identity. Yeah? Then you see that we come to this case. And here we assume that J equals, in this order, A plus I to the power of minus 1, B plus I to the power of minus 1 to handle this case. So both theorems will directly follow from Pearson's theorem, which we want to prove today. And yeah, in this proof, which is a little bit long, we will define operators W of t. You will see this in a few minutes in the following way: exponential ITA J exponential minus ITB. And of course, this is motivated from this definition here, why this object is interesting. And in particular, in the proof, we will need the difference W of t minus W of s, and we will see that this can be written in the following form: I times integral from s to t, exponential I UA C, exponential minus I UB du. Yeah? Yeah, this is clear. We simply take the integral over the derivative of this object, and if you compute the derivative of this, you will see that from differentiating this factor and this factor, you get the A and the B in two terms, and this exactly then yields to this operator C. Yeah? Do you see this? if you compute the derivative of this object, then you have to differentiate this term, then this gives a, and you can exchange the order of the operator a in the exponential, and then you have a second term where you get here the b with the minus sign, and you can again exchange the order, and then in the middle this yields to this term c. So that's why we obtain in the proof this formula, and then we will need compactness. So we need compactness of this term, and this motivates why we begin with the following lemma. So we start today with lemma 4.21, which exactly refers to this case here. So let A and B be self-adjoint operators so let A and B be self-adjoint operators, and let C be trace class. So C is a trace class operator. It's in V1 of H. Then we claim that then the operator K, which I define as follows. Let's do this on the other blackboard. Yeah. Then the operator K, which is defined by setting K phi to be simply the integral from 0 to 1 exponential I UA C exponential minus I UB du. And we define this for phi in H is compact. Yeah, and this is exactly what we will need in our proof later on. So it makes sense to look at the proof of this statement in this lemma here. Okay, proof. Okay, I take a sequence, let phi n for n in n be a weak null sequence. So let this with phi n converges weakly towards 0, and you know weak convergence implies boundedness, so we can assume that the norm of the phi n is, let's say, smaller than or equal to 1. Be given. Yeah, and we want to show compactness. This means that we have to show that the operator K turns the weak convergence of the sequence into strong convergence on the side of the images. That's what we have to show. So we show that. The supremum for norm of W smaller than or equal to 1 of the forms K phi n W, that this converges to 0 when I send n to infinity. And this will then imply compactness. Yeah, so assume that the norm of W is smaller than or equal to 1 henceforth. Okay. Yeah, given such an operator C, which is trace class, we know that this operator is in particular compact, and it satisfies the following. So given such a C, we can find a sequence of real values, lambda k, for k in n, and in particular, we assume in general in this chapter that these values are non-negative, so that the sum over these lambda k for k in n is bounded. This is the criterion that says that C is in the trace class. And then we also have the usual representation for compact operators. So we have orthonormal systems. And orthonormal systems. Two of them, let's say xn and yn. So xn for n in n and yn for n in n, such that we have the usual representation that C can be written as the sum over k in n. And here we have these singular values lambda k, and here the scalar product with the first orthonormal system xk, and here we have the yk. Yeah, this means that the operator C is trace class. Okay. Yeah, we now conclude that okay, let's start to compute. We have this definition of the operator k, as you can see it here. So let's compute the scalar product, first of all, of the operator that integrates from 0 to 1, exponential I UA. Here we have C, exponential minus I UB, and this is applied now to the phi n, as we are interested in this object here, du, and we compute the scalar product with this function w. What can we say about this? Let's continue here. Yeah, first of all, this can be rewritten in the following form. We have the integral from 0 to 1 over the scalar product exponential I UA, C exponential minus I UB phi n in the scalar product with the w, and this is integrated with respect to u. Yeah, now we can use the standard properties of these exponential groups here to rearrange this term in the following way. This is then C exponential minus IUB, and we get the adjoint operator on the other side. So this is exponential minus I UA W du. And the sense of this is that we can now plug in the representation of the operator C here. So we now can write that this is the integral from 0 to 1, and then we get here this sum k running through n, lambda k. And here I get the scalar product exponential minus IUB phi n with the first orthonormal system xk, and then we get here the yk in the scalar product with exponential minus I UA w. And this is integrated with respect to u. Yeah. And then we go on. And yeah, as the norm of this factor here, so if we take the absolute value of this, so as the absolute value of the scalar product yk exponential minus I UA W, what can we say about this? First of all, it is by Cauchy-Schwarz, can be estimated by the norm, the norms of both components. Yeah, but we know that this is an orthonormal system, so the norm is equal to 1, and this is unitary operator, and we assumed that the norm of the W is smaller or equal to 1, so this can be estimated by 1. And as this is the case, we conclude that, let's do it here. We then conclude that the integral from 0 to 1. Okay, let's take the complete term. So we have the absolute value of the scalar product of the integral from 0 to 1 exponential I UA C exponential minus I UB phi n integrated with respect to u, and this is the scalar product with the w. Yeah, the absolute value of this, which is our k phi n here in the first component, and this is then estimated by the integral from 0 to 1, sum for k running through the naturals, absolute value exponential minus IUB phi n xk du. Yeah? So we take the absolute value of the term that we have obtained here, and then we use that this second factor here can be estimated by 1. Sorry, the lambda k is missing here. Of course, this is missing. Yeah, then we obtain here the lambda k, which is non-negative, and the absolute value of this factor, which is remaining. This is correct now. Okay. Let's go on. Now, given epsilon positive, we can find a number n in n such that the sum for k bigger than n over this lambda k is smaller than epsilon. Yeah, this is clear. And then we let lambda be the maximum of the lambda k for k in n, so that we find that the absolute value of the scalar product of k phi n with this w can then be estimated by this lambda, and the sum for k running from 1 to n. Yeah, so we decompose it here over the integral from 0 to 1, absolute value of the scalar product of exponential minus IUB phi n with our w du, and the other terms for k bigger than n simply can be estimated by epsilon. Yeah, this comes from this condition here. And of course, the norm of this scalar product is simply estimated by 1, and the integral is from 0 to 1. So we simply have epsilon here remaining concerning the other term. Yeah, so now we need one final argument. Yeah, basically there are different ways to prove this, but let's do it like this. For any k in n, and all u in the interval from 0 to 1, and we have that the scalar product exponential minus I ub phi n with this w, with xk, sorry, this has to be corrected here. This should be xk, yeah. It's a spelling mistake, this comes from here, yeah. So I've decomposed this into two parts. First of all, the sum from 1 to n, and then I have taken the maximum of the lambda k in front of the integral and the sum. So this has to be xk here, and the remaining term for k bigger than n, as I had explained, can be estimated by epsilon. So we have here this term that we have to discuss. Yeah, but what can we say about this? This is nothing but the scalar product phi n with exponential iub xk, and we know that this converges to 0 when we send n to infinity, because the phi n are a weak null sequence. So we know that this convergence holds true, and then by Lebesgue's dominated convergence theorem, so by Lebesgue's dominated convergence theorem, we then obtain that the integral from 0 to 1 over the absolute value of the scalar product of exponential minus I ub phi n xk du, this then converges to 0 when I send n to infinity. And if you look to the other blackboard, you will see that this is exactly this term here, yeah? And we have a sum which is finite, so there's absolutely no problem. So let's take it all together. Yeah, basically we don't have to say anything. I think this is clear from this point. This will converge to 0, and we have epsilon remaining, and epsilon was arbitrarily small, so this already achieves the proof. So this completes the proof. And then we are done here. Okay. One remark that refers to this argument that I had presented here. Maybe this is also interesting to see. Remark 4.22. Yeah, in the proof of lemma 4.21, yeah, we could also use the following argument. We could also make use of the compactness of the following sets. Of the compactness of the sets let's say mk, which I define as the images of the xk under the exponential map, so exponential iub xk for u ranging between 0 and 1. Yeah, and as this interval from 0 to 1 is a compact set, and the exponential map is continuous, the mk will also be compact. Yeah, so this is, these sets are compact. Yeah, which follows from the compactness of the interval from 0 to 1 and the continuity of the map that sends u to exponential minus iub. Yeah? And if we use that these sets are compact, hence we obtain that the convergence of the phi n with some element z belonging to this mk, so phi n times z, this will then converge to 0 for n to infinity uniformly for z in mk. And then you can proceed as we had seen here on the left-hand side. Okay, now let's come to Pearson's theorem. That we state now. This is theorem 4.23. Theorem 4.23, Pearson's theorem. Which contains the following statement. So let A and B be self-adjoint operators. Self-adjoint operators with the same domain. So with d of A is equal to d of B. Let J be a bounded linear operator. Let J be a bounded operator so that the operator C that I define as a J minus JB is trace class. This is the condition 4.1. We will meet this in the following. Then we claim here, then the strong limits. These modified, in some sense, wave operators, so omega plus minus a bj that are defined as the strong limits for t going to plus or minus infinity exponential I ta, and here the j in between exponential minus I ub, t, and the projection PAC of B exist. Yeah, before we come to the proof, which is a long proof, I would like to remark two things. So we have remark 4.24 here. Remark 4.24. First of all, as I already said in the introduction, we will apply Pearson's theorem with the setting that J is equal to the identity, so that the operator C turns to simply A minus B, and then we assume that this is trace class. And then you also see that we get the normal wave operators that we already know from this definition here. For the Kato-Rosenblum theorem, and we will also set J to be A plus I resolvent times B plus I resolvent to obtain the Kuroda-Berman result. Yeah, you can imagine what will happen. Yeah, if you simply compute this expression here, you obtain, so this is a note here, A applied to A plus I resolvent B plus I, and the resolvent minus, and then this operator here, and then the B. You can, of course, now do the following. We can add here plus I and minus I. And we can also do this here. So here we have A plus I minus I here. And if you do this, you will see that, yeah, first of all, this term here will cancel out, so that we have simply the B plus I to the power of minus 1. So we have here the B plus I to the power of minus 1. And what is remaining is minus I times this, yeah, let's say J. Yeah, we can simply write J. And here on the other side, we have minus, and here this term cancels out. So here we have A plus I to the power of minus 1, and minus simply gives plus I times the J. So this term then here will cancel out. And we have then the assumption that B plus I to the power of minus 1 minus A plus I to the power of minus 1. And this then has to be a trace class and will yield to the Kuroda-Berman result that I presented in the introduction to this section. So this is the idea why we apply the theorem to these two cases. Yeah, and another remark, number 2. It refers to the assumption 4.1, remark number 2. It says the assumption 4.1 in Pearson's theorem should be understood in the following way. So it should be understood in the following way. For phi in the domain of B, which is according to our assumptions, equal to the domain of A. J phi, J is a bounded operator, and then J phi is again in the domain of B and then also in the domain of A. And the closure of the operator AJ minus JB, and this operator restricted to the domain of B, is trace class. Yeah, so this is important to note. Okay, then we can begin with the proof. I think that we will not be able to see the whole proof in the rest of the time today, but I will begin with the proof and explain the remaining steps so that you will be able to find the connection when we restart with this next time. Okay, so let's look now at the proof of theorem 4.23. Okay. Let's write, so we write W of t. This should be the operator exponential ITA. Here's our operator J, exponential minus ITB. And then we consider the strong limit of this object for t going to infinity. And consider the strong limit of W of t for t going to infinity. Yeah, now we have to recall theorem 4.18. So recall theorem 4.18. And there we had defined a set M of B, script M of B. This was the set of all phi in HAC of B, such that there exists a number R positive, and there was a function f, which was also bounded, such that we had the following properties. So furthermore, with the property here that the support of f, this compact support, is contained in the interval from minus R to R. And such that we had that the spectral family, the operators E belonging to the operator B, satisfy that E of minus R phi is 0 and E of R phi is phi, and such that we have for the spectral measure that this was given by this density here. And lambda simply was the Lebesgue measure. You recall this, yeah? That's what we had in theorem 4.18, which said that the subspace M of B is dense in HAC of B with respect to the usual norm on the Hilbert space H, so that hence it suffices to show that the limit for t to infinity of w of t phi exists for all phi in M of B. Yeah, and what does this mean? I think, yeah, we will state this on the other blackboard. Let me first of all clean the blackboards, and then I state what we have to prove. Yeah, we want to show that the limit for t to infinity of this w of t applied to phi, for phi in the MB space, that this limit is 0. And thus we have to show that the following limit is 0, the limit for t to infinity taken over the supremum for s bigger than t of the difference w of s, or let's say w of t, minus w of s applied to phi for phi in M of B to the power of 2 is equal to 0 for all phi in M of B. That's our goal now. And yeah, I will do this in several steps. And we begin now with step number 1. First of all, let x be some bounded linear operator on H, then the map that sends, or that goes from R to the L of H, and that sends t to exponential ITB x exponential minus ITB. U is strongly continuous. For all u in H. For any u in H, which simply follows from the properties of these strongly continuous unitary groups, these exponential groups here. Yeah, in particular, what does this mean or imply? In particular, we find that the Riemann integral let's say FAB of x, this is my notation applied to u, which is defined as the integral from a to b exponential minus ITB, plus ITB here, x exponential minus ITB applied to u, and this here integrated with respect to t for a smaller than b. This Riemann integral exists and defines a bounded linear operator, and defines an operator FAB, referring to these boundaries A and B of x, which is in L of H. Yeah, and now we prove the following identity, which will take a little bit of time. Let us now prove that W of t star W of s minus exponential IAB W of t star W of s exponential minus I AB. This is nothing but f 0a of y of t and s, where this y is given by the following expression, where y of t and s is defined by minus I. This is a factor here. And then we have exponential ITB, J star, exponential minus I, T minus S, A, C, exponential minus I, S, B, minus, and then a second term, maybe we'll write it down here, minus exponential ITB, and now C star, exponential minus I, T minus S, A, J, and exponential minus I, S, B. And this together is 4.2. So let me check that this is correct. Exponential minus I, exponential ITB, J star, exponential minus IT minus SA, C, exponential minus ISB, minus exponential ITB, C star, exponential minus IT minus SA, J, exponential minus ISB. Okay, that's our task now. So let's do it. So let Q of B be defined by exponential IBB, W of T, star, W of S, exponential minus IBB. Yeah? And then we compute the derivative of this object with respect to B, to small b. So then we find that. Okay, now let's compute it. dB of Q of B. Let me first of all write down the result, and then I will explain the steps. This is simply I, exponential IBB. And then, of course, we get two terms, because we have, first of all, a differentiation in this argument, and then the rest leaves as it is, and then we get a second term where we apply the differential operator here. So we get two terms, and the first one is B, exponential ITB, J star, exponential minus I, T minus S, A, J, exponential minus I, S, B, and the second term minus exponential ITB, J star, exponential minus I, T minus S, A, J, exponential minus ISB, B, and exponential minus I, B, B. Okay, where do all these terms come from? Okay, first of all, we have here this W of t here. You know that from the definition, this is nothing but exponential I TA, J exponential minus IT B. Yeah? Then we have here Okay, well, let's first of all go through the first computation. We compute the derivative with respect to b for this factor, then we get 1b as a factor here, yeah? Okay, so this comes from the derivative. And if we take the adjoint of this red object here, then you will have to change the order. So you have exponential plus ITB here because we have taken the adjoint. This is here. Then we have J star. And here you get then a minus sign. So this is exponential minus ITA. And the rest, this exponential plus ISA, J, exponential minus ISB is simply this, W of S. Do you see this? This is the W of S. And the rest here stays the same. And in the second summand, we have the differentiation for this factor here. So we get a minus sign. And again, the operator B, which stands here. And then we do the same arguments. We get the adjoint of this red object, which is here, and the W of S, which is also the same here. So this is correct. Can you follow this? Okay. So we have these two terms. Okay. And now as JB is nothing but a J minus C. This simply comes from the definition of the operator C, which was defined as AJ minus JB. As this is the case, and we can take the adjoint, then we get B, because B is self-adjoint. J star is equal to J star A, which is self-adjoint, minus C star. We find that that we get B exponential ITB J star. What is this? Here we can, according to the spectral theorem, change the order of these two operators. So this is exponential ITB B J star, but this can be replaced according to this relation here, exponential ITB, and then we get J star A minus exponential ITB and C star. And furthermore, we get that J exponential minus ISB B, again by the same argument. First of all, we exchange the order of the two operators so that we get JB exponential minus ISB. And this is then, according to this relation, it's a J exponential minus ISB minus C exponential minus ISB. Yeah, and then we can replace terms in our derivative here. Hence, we find that the derivative ddB of Q of B then is, first of all, I write it down, I exponential IBB, and then we get now 4 terms because each term that we replace will give 2 new terms, so that we have here exponential ITB, yeah, J star A, exponential minus I, T minus S A, J exponential minus I S B, this is the first one, minus exponential I T B, C star, exponential minus I T minus S A, J exponential minus ISB. Then we get minus exponential ITB, J star, exponential minus I t minus s, A, aj exponential minus I s b, and finally plus exponential ITB, j star exponential minus I t minus s a c exponential minus I s b, and this times exponential minus I b b. Okay, where do all these terms come from? Okay, let's begin here. We have here this first term and this term here. And we find them in our result here. And here. Yeah. And then we have this term and this one. And we find them here and here. And then you see what I have done. Yeah, here in this first term, I have replaced these two terms so that if you follow both equations, we get exactly what we have here on the right-hand side. Yeah, this is correct. This comes from, the first two terms come from the replacement of this object here, and the second two terms come from the replacement here below. Here I have replaced this term. Yeah, so this is what I had replaced, and here I had replaced this. And if you take care of what I have done, I think it's correct. Yeah, and this is the second term. It has to be exactly with plus because we have a change of the sign here. Okay, all right? Can you follow it? Okay. Now, using that exponential minus I t minus s a is the same as a exponential minus I t minus s a, we see that the first and the third term cancel out. Yeah, look at the first and the third term, where we have simply the change of the order of these two operators, and they have a different sign, so they will cancel out. And this means then that, we obtain the following result. Yeah, so that ddB of Q of B simply is minus exponential IBB times y of TS and exponential minus IBB. Please simply check this with the definition of the y that I had given you in definition 4.2, in formula 4.2, and then you will see that with this definition, if you take together the remaining terms, so this one and this one, you will see that this exactly gives the y of t and s, as I had defined it. So we get this result here. Yeah, and then finally, we find that W of t star W of s minus exponential I AB W of t star W of s exponential minus IAB. This is the term that we are interested in. Yeah, but what is this then? This is nothing but Q of 0 minus Q of A. When you look back to the definition of the Q, then you get exactly this difference here. And this can now be written as an integral minus the integral from 0 to A over the derivative of Q with respect to B as a function of B dB. But now we can replace what we had obtained here, so that this is nothing but the integral from 0 to A exponential I BB y of t and s and exponential minus I BB dB. And according to my definitions, this is nothing but this f of 0 and A. This refers to the boundaries. And then we have the sandwich here, and in the middle we have the operator that we placed here in brackets. So this is of y and t and s. And this was exactly what I claimed. So this is step 1. So we can now come to step 2. Yeah, as in the proof of Cook's theorem, there you can look up the formula 3.5. We now use that W of t minus W of s, as I had explained in the introduction, is nothing but I times the integral from s to t exponential I UAC exponential minus I UB du. And this is now where we apply this lemma with the compactness by lemma 4.21. The difference W of t minus W of s is compact. And then applying lemma 4.20, we get that the limit for a to infinity of the norm of exponential IAB W of t star applied to W of t minus W of s exponential minus I AB phi. This limit is 0 for any phi in the M of B. Why? Because we had shown in this lemma that for phi in this subspace, this here converges weakly towards 0. You recall this? And here we use that this difference operator is compact. And then the norm of this will converge to 0. Yeah, and now equation 4.2. Equation 4.2 shows that. Let's continue here. it shows that W of t star applied to W of t minus W of s, this is nothing but F0A of y of t and t minus y of t and s. And there's another term remaining. So plus exponential IAB W of t star applied to W of t minus W of s exponential minus IAB, sorry. This is simply from 4.2, so that yeah, exactly. So that for phi in M of B, we conclude that the scalar product phi with W of t star applied to W of t W of s phi, this is then nothing but the limit for A going to infinity of the scalar product phi with f of 0 and A y tt minus y ts applied to phi, which is equation 4.3. Yeah, because this term here, this second term here, converges to 0 when we send A to infinity according to this observation here. So this is what we achieve. Okay, and finally, I would like to stop with the statement of step 3, and we will see the proof of the details of this in the next lecture. So as C is trace class, we have the representation that C is simply the sum for k from 1 running to infinity, or here I've taken n. Okay, lambda n scalar product with sum phi n times psi n, where the lambda n are positive. The sum over the lambda n is finite, and phi n and psi n are orthonormal systems. Yeah, in this step, we claim that if X is a bounded operator and A is positive, then we have that the absolute value of the scalar product F0A of exponential IUB x exponential minus IUB applied to phi times phi, this absolute value can be estimated in the following form, and this is where I would like to stop, by 2 pi the norm of C in B1 of H and the square root of this times the operator norm of X times the triple norm of phi, which is simply the an infinity norm of this density f that belongs to the phi because it's an M of B, and times the following square root, sum n in n, lambda n, integral from u to infinity, and here we have the absolute value of the scalar product, phi n with exponential minus I x b phi to the power of 2 and integrated with respect to x. This is 4.4. And here I would like to stop. Maybe I give you an outlook. We will prove this in the next lecture. And today I will only give an outlook to the final steps of the proof. So we have the following idea then. Idea of the proof. And we will see the details then in the next lecture. We will see that the difference w of t minus w of s the norm of this to the power of 2, I think here the phi is missing, sorry. Like this, yeah. We will see that this can be estimated by terms of the form that we have the absolute value of the scalar product of f of 0 and a, y of q and r, phi times phi. And then we use, when we have this estimate, we use, of course, the estimate 4.4 that we will prepare in step 3. And we use here the definition then of the y. This a little bit complex definition. And we will use estimate 4.4 to obtain that this difference here in the norm converges to 0 for s bigger than t and t is sent to infinity. So this is in some short steps explained what we will do next time, what will achieve the proof then. And in the next lecture, our first goal will be to provide a proof of this estimate, which will be crucial, and then the rest will follow by the arguments that I had presented there in a short form. Okay, I thank you. We now take a short break and continue with the exercises, and then we are done for today. Thank you.